हेलो एंड वेलकम अगेन टू फिजिक्स गैलेक्सी। आज हम प्रीवियस ईयर नेट एग्जाम का एक क्वेश्चन कर लेंगे। ओके, एंड द क्वेश्चन इज अ बीम ऑफ लाइट ऑफ फ्रीक्वेंसी ओमेगा is reflected from a dielectric metal interface at normal incidence. The refractive index of the dielectric medium is n, and that of the metal is given by this complex number n into 1 plus iota rho. If the beam is polarized parallel to the interface, then the phase change experienced by the light upon reflection is. So we have to find out what is the phase change, okay, when light is being reflected from the interface of dielectric and metal. Okay, so let me give you a brief review of this reflection from metal dielectric interface first, and then we'll solve this question. Okay, so basically हमारे पास एक and left hand side I have on the left hand side I have dielectric medium, and that I will call medium number 1, and on the right hand side I have metallic medium, so metal, and that I will call medium number 2. Okay, and my coordinate system is like this. So this is my z direction, and this is my x direction, and my y direction is coming out of this screen. Okay, and first of all what I will write all the fields, that is the incident field, reflected field, and the transmitted field. So suppose this is the incident light, and suppose this is the reflected light, and this is my transmitted light, so suppose. Okay, so first of all what will be incident? Incident will be simply the uh, incident amplitude, that I will write as E naught I times the exponential part e to the power iota, because we are in medium 1, so I'll write k1, and it's propagating in the z direction, so k1z minus omega t. And for the reflected light, okay, and we're assuming here that the uh, electric field is oscillating in this direction. Okay, it's parallel to the interface. So for the reflected light, the electric field will be written as ER equals to E naught R, that is the reflected amplitude, e to the power iota. Now what about the k vector? K vector will be opposite of k1, so I'll write minus k1z minus omega t. And for the transmitted light, I'll write ET equals to E naught t, that is the transmitted amplitude, e to the power iota k2, because we're in medium 2 now, k2z minus omega t. Okay, and also I will write the magnetic fields, corresponding magnetic fields. So for the instant light, bi will be equals to, now the amplitude of the magnetic field will get reduced by a by v1, that is the speed of light in medium 1, so I'll write e naught I divided by v1, where v1 is the propagation of speed of propagation in medium 1, and the same factor exponential. Okay, and similarly for reflected light, magnetic field can be written as br equals to same thing, amplitude of electric field divided by the velocity of light, so I'll write E naught R upon V1, and the same exponential factor. But one thing about this reflected magnetic field is that magnetic field will suffer this phase change of pi, so that I will denote all that I will write by putting a minus sign here. Okay, and for the transmitted magnetic field bt will again be written as E naught t divided by the velocity of light in this medium, that is v2, and the same exponential factor. Okay. Now because we have to find the phase change, and we know the phase changes occur at the interface, so what will we do? We'll solve our boundary conditions at the interface. Okay, and let me write down the boundary conditions first of all. So for the electric field, we know the parallel components must be equal, or parallel components must be continuous across the interface. So I will write E1 parallel equals to E2 parallel. Okay, so this is the boundary condition for the electric fields. And for the magnetic fields, we know because there are no surface currents, so the parallel components of the magnetic field will also be continuous. So I'll write B1 parallel by mu1 equals to B2 parallel by mu2. Okay, now what about what is E1? E1 is the electric field in the electric medium. E2 is the electric field magnetic medium. Let me write down the corresponding values. But before that, one thing you have to know, that is we are solving our boundary conditions for z equals to 0. Okay, so that means this term, this term, this term is 0, and e to the power minus omega t, here also e to the power minus omega t, here also e to the power minus omega t will be common, so we won't bother about e to the power minus omega t. So now let's write down, we just have to only write down the amplitudes. Okay, so E1 parallel, so E1 parallel means the electric field in the dielectric medium, because there are two parts, one is the incident and the reflected one. So I will write E naught incident plus E naught reflected. Okay, so this is the electric field in the medium 1, and electric field in medium 2, it's single, that is E naught transmitted. This is our first equation, equation 1. What about magnetic field V1? So I'll write 1 by mu1. V1, we have to write two parts, one is the incident magnetic field amplitude and the reflected magnetic field amplitude. So incident magnetic field amplitude is 1 by E naught I by V1. So I by 1, and the reflected magnetic field amplitude is this one. So there is a minus sign, so I'll write minus E naught R by V1 equals to, and what about the transmitted magnetic here, 1 by mu2 E naught T divided by V2. So I will just follow it a bit, so it will be 1 by mu1 V1, and then it's E naught I minus E naught R equals to E naught T divided by mu 2 V2. Okay, or I can write the two equations, the first equation and my second equation will be E naught I minus E naught R equals to this mu1 V1 can transfer to this side, so it will become mu1 V1 divided by mu2 V2, and then it's E These are my two. Now I won't solve these two equations because simply just first subtract them, then add them, and you will get two equations, okay, relating reflected amplitude with the incident amplitude. So I will write simply E naught R equals to 1 minus, first of all I will write this factor as beta. So when you will solve these two equations, you will get 1 minus beta divided by 1 plus beta times E naught incident. Okay. Second equation you will get E naught transmission, or T equals to 2 times 1 plus beta E naught. Okay, so these are the two equations you have to always remember. So this is for the reflection, okay, and this is the transmitted amplitude. So if you know what is the incoming amplitude of light, you can figure out what is the reflected amplitude. Similarly, if you know incident amplitude, you can find out the transmitted amplitude. And there is also the information of phases. Now because we have to only find the phase change in the reflected light, so we'll use only this equation. Okay, so this equation we'll be using for to solve our question. So before that, what I will write down, so this beta, which equals to mu1 v1 upon mu2 v2. Okay, now one thing you have to always remember, that is for most of the optical non-magnetic materials. Okay, so if you have optical non-magnetic materials, you'll find that this mu1 mu2, they are almost equal to mu naught. Okay, there is no um, large difference. Okay, mu1 and mu2 is almost equal to mu naught, so you can write this almost equal to v1 by v2. Okay, so remember, this is not the case for magnetic materials. If you take iron or nickel, cobalt, this won't be the case. But for most of the optical non-magnetic materials, you can always approximate beta as v1 by v2. Okay, and we know, so that means beta can be written as, suppose, v1 by v2, and in terms of refractive index I will write as n2 by n1, because refractive index is inversely proportional to the velocities, so n2 by n1. Okay, so that means my equation will, okay, so now what do I have to find, basically phase change, right? So we'll go to this equation, not E naught R equals to 1 minus beta divided by 1 plus beta times E naught incident. Now beta, as we have already written as 2 by n1 n2. So n2 here means the refractive index of the metal divided by the refractive index of the medium, electric medium. So n2, that is given already in the question, that is refractive index of the metal is given by n times 1 plus iota rho, and for the medium it is given by n. So I will put the values, so it will be n 1 plus iota rho divided by the refractive index of the dielectric medium, that is simply given by n. So n cancels out, so beta will be given by 1 plus iota rho. So if I substitute here, it will become 1 minus iota rho, so it will become minus iota rho divided by 1 plus iota rho, that will become 2 plus iota rho. Okay, now this equation not only contains the amplitude information, it also contains phase information. So to deduce that phase information, what we'll do, uh, we'll look at this factor. So iota minus iota rho, okay, divided by 2 plus I. So it's a in general complex number, and if we want to find the phase, so find out the phase, what we'll do, we'll multiply with the complex conjugate, the denominator and in the numerator. Okay, so we'll multiply with the complex conjugate of the denominator, 2 minus iota rho, and then 2 minus iota rho in the denominator as well. So it will become minus 2 iota rho minus minus plus iota square go minus rho square divided by, it will be simply 4 plus rho square. So this is my complex number. Okay, and I had to find out the phase of this complex number. So phase of this complex number is simply the imaginary part. Okay, so we know that tan of phi is given by the imaginary part, and imaginary part in this case will be 2 minus 2 rho divided by 4 plus rho square, which will get cancelled out, so divided by rho square. Okay, or you can write tan of phi equals to, sorry, there is minus again, so minus minus cancels out, 1 row cancel out, it's simply tan of phi equals to 2 by rho. So this is the phase for this equation. Okay, this equation, the tan of phi. So to get the phase, we'll write phi equals to tan inverse of 2 by rho. So basically what I did, I